For over a century, global telecommunications ran on the movement of electrons through copper wire. Today, the core of our digital infrastructure relies on a completely different physical mechanism, the transmission of photons through glass. In the framework of the Open Systems Interconnection model, this transition happens exclusively at Layer 1, the physical layer. While higher layers handle software routing or application logic, Layer 1 has a singular responsibility, translating digital ones and zeros into physical phenomena. In an optical network, that means converting electrical voltage into distinct intensities and frequencies of light. There is no software logic here. It manages raw, unformatted bitstreams. It does not read IP addresses, it does not route packets, and it offers no error control. Because there is no safety net built into this level, the hardware itself must be flawless. Any physical anomaly, whether it's a microscopic scratch on a connector or a timing misalignment causing a buffer underrun, results in permanent data loss before the higher layers even know a transmission occurred. To understand how modern networks achieve terabit scale throughput, we have to look past the code and analyze the optical physics, the media architecture, and the precise diagnostics required to maintain these systems. The reliability of the entire internet ultimately rests on the mechanical precision of injecting raw logic into a beam of light. The primary engineering challenge in an optical network is distance. You have to send a beam of light through a glass strand and prevent any photons from escaping over hundreds of kilometers. The solution relies on a principle of optical physics called total internal reflection, which allows a waveguide to contain and direct light with near-zero signal loss. To achieve this reflection, a fiber optic cable is constructed with two essential layers, an inner core where the light travels, surrounded by an outer layer called the cladding. This diagram shows the cross-section of a fiber strand. The core is high-purity silica glass with a specific refractive index. Crucially, the core's refractive index is manufactured to be slightly higher than the surrounding cladding. The interaction between these two distinct materials is governed by Snell's law. When a light ray traveling through the core hits the boundary of the lower index cladding, it splits. Part of the light reflects inward, while the rest refracts, escaping into the cladding. But as the angle of the incoming ray widens, the escaping refracted ray bends closer to 90 degrees, eventually grazing the exact boundary line between the two layers. The moment the incoming light exceeds this specific threshold, known as the critical angle, refraction stops entirely. No light passes into the cladding, and the entire ray bounces back into the core, achieving total internal reflection. Because light must hit the boundary at this steep angle to survive the journey, it must be injected into the cable at a specific trajectory. This mathematical range of acceptable entry angles projects outward from the fiber face, forming a cone known as the numerical aperture. Any light injected outside of this precise geometric window will hit the core boundary at too shallow an angle, fail to reflect, and immediately bleed out into the cladding. While total internal reflection defines how a fiber works, the physical diameter of the core dictates what it is capable of. This calculation represents the V number, or normalized frequency. By comparing the diameter of the core against the specific wavelength of the transmitted light, engineers can determine exactly how many independent paths, or modes, the light can take as it travels. When manufacturers shrink the core to a microscopic 8 to 10 micrometers in diameter, the V number drops below 2.405. The geometry becomes so tight that the light is forced into a single, straightforward path. This configuration is categorized as single mode fiber. Because the entry target is incredibly narrow, it requires highly coherent, precision laser light sources to successfully inject data. Forcing light down one solitary path completely eliminates intermodal dispersion, the temporal spreading of pulses that occurs when light rays take different routes. Without this distortion, the network can push terabytes of data over vast geographical distances. If we increase the core variable to 50 micrometers, the V number spikes. The single beam splinters into multiple modes, with different light rays zigzagging and bouncing through the wider core at varying angles. This wider design is known as multi-mode fiber. A 50 micrometer core presents a much larger target. This allows network operators to use significantly cheaper, lower precision light sources, like vertical cavity surface emitting lasers, or VCSELs, reducing overall hardware costs. However, the multiple paths create a severe operational limit. Because a light ray bouncing at a steep angle travels further than a ray moving straight down the center, the pulses arrive at different times. Over long distances, they smear together, completely corrupting the data. The difference between a 9-micron and a 50-micron core dictates the hardware budget, specific transceiver requirements, and maximum physical reach. Inside a hyperscale data center, these strict physical limitations dictate the architectural layout of the server racks. Modern facilities utilize a spine-leaf topology. In this 2-layer design, every spine switch in the top row connects directly to every single leaf switch in the bottom row, creating a non-blocking mesh that minimizes latency for massive server-to-server traffic. This layout relies on specific media matched to precise distances. At the lowest tier, connecting servers within the same rack, the cables rarely exceed 5 meters. At this microdistance, operators deployed direct attach copper cables. Copper is heavy and susceptible to interference, but over 5 meters, it offers near-zero power consumption and ultra-low latency. Moving up to the second tier, we find short-reach connections spanning between 5 and 100 meters across the facility floor, linking the leaf nodes up to the spine. Here, the network switches to OM4 or OM5 multimode fiber. The distances are short enough to avoid severe modal dispersion, allowing operators to achieve high bandwidth while capitalizing on the cost efficiency of VCSEL transceivers. Finally, we reach the interconnects that extend beyond 100 meters, managing traffic that exits the spine and flows into the wider campus or global backbone. At these distances, OS2 Single Mode Fiber takes over completely. Only the precision of a cohesive laser beam traveling down a microscopic core can push 100 gigabit traffic across kilometers without signal regenerators. A data center is a highly engineered mosaic of physical media, where copper, multimode, and single-mode fibers are deployed strictly according to their absolute distance limits. Maintaining this Layer 1 infrastructure introduces unique security profiles and physical vulnerabilities completely distinct from software networks. Unlike copper cables, which emit electromagnetic radiation that can be passively recorded by nearby antennas, optical fiber transmits photons through non-conductive glass. Because it emits zero electromagnetic interference, traditional wireless eavesdropping is physically impossible. To physically tap a fiber line, an attacker must resort to macrobending. By bending the core into a sharp curve, they alter the light path's geometry, forcing photons past the critical angle so they leak out through the cladding boundary to be captured. However, diverting light away from the core immediately degrades the transmission power. Modern network management systems continuously monitor for these sudden drops in intensity, detecting the physical intrusion the moment the cable is bent. Intentional tapping is rare. The overwhelming majority of signal loss comes from microscopic contamination. A single speck of dust or a smudge of skin oil on a connector end face will severely scatter the incoming light. To locate these microscopic faults over immense distances, technicians use Optical Time Domain Reflectometry. This graph displays an OTDR trace. By firing intense light pulses down the cable and measuring the light that bounces back, the device plots distance on the x-axis against signal loss on the y-axis. The gradual downward slope represents the intrinsic attenuation of the glass itself. When the trace shows sudden, sharp vertical spikes, the OTDR has detected Fresnel reflections. These spikes occur precisely where the light hits an abrupt change in the refractive index, pinpointing the exact location of a dirty connector, splice, or severed cable. Managing this infrastructure requires relentless attention to the physical layer, where a misaligned microscopic geometry or a fingerprint can sever terabits of throughput. As artificial intelligence and cloud computing place massive demands on hyperscale data centers, network architects are pushing physical layer hardware from 400 gigabit speeds up to 800 gigabits and 1.6 terabits. To achieve these data rates, operators utilize advanced modulation schemes like PAM4, which encodes multiple voltage levels to pack twice the data into the exact same spectral bandwidth. Yet, even with highly optimized modulation, the physical medium is becoming a bottleneck. Light naturally travels about 30% slower through solid silica glass than it does when moving through a vacuum. To bypass this limitation, engineers are developing hollow core fiber. By engineering a cable that forces the light to propagate through an air-filled or vacuum center rather than solid glass, network designers can strip away the refractive drag and drastically reduce end-to-end latency. While the era of copper networking hit hard physical limits regarding heat and interference, optical infrastructure is bounded only by our mastery of light. By refining the geometry of glass and the manipulation of photons, fiber optics provides a boundless foundation for global digital expansion.